Hey guys, part 2 in our video series on rates of change. So we're working on the same problem, and an object is falling and it's modeled by y equals 16t squared. We want to find the instantaneous rate of change at 3 seconds. Before we were finding the average rate of change, where you just use the slope of a secant line. When we want to know the instantaneous rate of change, so how fast it's moving at exactly 3 seconds, that's when we're going to look at the tangent line. So let's get an idea of what this picture looks like. We had our parabola, y equals 16 t squared. We want to know at 3 seconds. So when we're out here at 3, what is the rate of change of this object? So basically we want to know what is the slope of the tangent line. But how do we find slope if we only have one point? So we're going to look at it two different ways. We're going to look at a numeric approach and then an algebraic approach. The numeric approach is going to be if you have a calculator and just kind of get a really, really good approximation. And then we're going to talk about the algebraic way where you can get the exact answer. But basically we need to find the slope of this tangent line, and that will tell us the instantaneous rate of change. Okay, so again, we're going to start with the numeric approach, which is where we're going to use our calculator. So we're going to consider a couple of different cases. Let's talk about right before 3 seconds, right after 3 seconds, and then if we use both of those points and go right around 3 seconds. So let's look right before 3 seconds. We would have the point 2.999, and then that would be 143.904 or something. Use your calculator. And then the point at 3, if I plug in 3 into this equation, I'm going to get 144. So we were at this point right before 3, and then we're at this point at 3. So what is the slope right in between those 2 points? So I can just do a slope calculation. I'm not going to write it all out, but you would get 95.984 feet per second. So right before 3 seconds, its instantaneous speed, or its approximate instantaneous speed, would be 95.984 feet per second. Right after it, we're going to do the same thing. We're going to look 0.001 seconds after 3. So the first point we're going to use is going to be at 3 and 144. The second point is going to be 3.001 and 144.096, and then there's some more decimals. All right, again, if I do a slope calculation here, I would get 96.016 feet per second. Close, but not exactly the same thing. And then if we think about, okay, let's not actually use the point that's at 3. Let's use this point that's just before it and this point that's just after it. So we can do 2.999, 143.904, and then 3.001, 144.096. And if I calculated the slope there, I would get 96.000 feet per second. These are all very, very close. So I have a pretty good idea that the instantaneous rate of change, the exact instantaneous rate of change, is going to be 96 feet per second. And we'll find that out algebraically in a second. So again, to summarize what we just did, to try to find the instantaneous rate of change, since we can't find the slope just at one point, we looked at a point just on this side of it and another point just on the other side of it. And then we calculated a couple of different slopes. So the slope going through these two, the slope going through these two, and then the slope going through the outside two. And they were all very, very, very close. All right, so now let's look at the algebraic, which will give us the exact value. So to find the instantaneous slope, you can't just use the slope calculation of 2 points because we only know one of the points. It's going to ask you at t equals 3, for example. So let's think about any given curve. So I've got some point where I've got x, and then let's just call this any curve. So this is going to be f of x. This is my f of x function. So if this is x, this would be the point f of x. And then let's go over some distance on the x-axis. Let's call that h to find a new point. So if this is x, then this new value over here is x plus h. Let's call this my x1. This is going to be my x2. So x1 is just x. x2 is x moved over by a value of h. And then the y value here would be the function with this x value plugged in. So f of x plus h. So this would be my y1 and my y2. So the y1 goes with x1, y2 goes with x2, and we want to find the slope going in between these. So the slope, y2 minus y1 over x2 minus x1, which would be f of x plus h minus f of x over x plus h minus x. And then we have x plus h minus x, so these x's could cancel out, which would just be f of x plus h minus f of x over h, which is basically just saying take this distance, so subtract those two, and divide it by the x distance, which is h. Now, instantaneous slope would mean that this point needs to get closer and closer and closer and closer to our original point. Basically, the distance between them needs to shrink and shrink and shrink and shrink and shrink until h is 0. But h can't actually be 0 because then I'd be dividing by 0. So I just want to get really, really, really close to 0. So the distance between these 2 points is going to get really, 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 really close to 0. And the way we would say that is we would say the limit as h approaches 0. So we're going to put it all together on the next slide to find the instantaneous rate of change. So the speed at an exact time, or the velocity at an exact time, depending on the problem. To find the instantaneous rate of change, you're going to use the slope of the tangent line. Now, at this point in the course, the way we're going to figure out the slope of the tangent line is using this formula. The limit as h approaches 0 of f of x plus h minus f of x divided by h. So, again, in your notes, this is a really big one. So, instantaneous rate of change is the slope of the secant line. In the previous video, we talked about how the average rate of change was the slope of the secant line. Okay, let's look at this this specific problem we were working on back here, the algebraic way. So, going back to my original problem, y equals 16t squared, and I want to know what is the instantaneous speed at t equals 3 seconds. So in order to do that, I'm going to use the equation I just had, the limit as h approaches 0 of f of x plus h minus f of x over h. So we're going to take 2 points, the distance between them being h, and we're going to shrink that distance until there is no distance between them, and we're going to find the slope going through those 2 points. All right, so off to the side, f of, in this problem, we don't have x, we have t. So this formula is going to change to the limit as h approaches 0 of f of t plus h minus f of t over h, because the variable here is t instead of x. So f of t would be 16t squared, meaning that f of t plus h would be 16 times t plus h squared. And then let's go ahead and simplify this. So it'd be 16 times, if I multiply out t plus h squared, it's not just t squared plus h squared, it's going to be t plus 2th plus h squared. Make sure you actually multiply it out, and then distribute the 16, so it'd be 16t squared plus 32th plus 16h squared. So let's plug in my f of t and my f of t plus h into this formula. So we've got the limit as h approaches 0 of 16t squared plus 32th plus 16h squared. That whole thing is f of t plus h minus f of t, which is 16t squared. That's my f of t. Whole thing divided by h. So whenever I have a limit, I want to see if I can just plug in h. Now the problem is I'd be dividing by 0, so I can't plug in h right now. So let's see if we can simplify. I have a positive 16t squared and a negative 16t squared, so those can cancel out. So this becomes the limit as h approaches 0. Cancel these out, and I would have 32th plus 16h squared over h. Again, I just canceled those out. And then I can pull out an h on the top, because right now I'm still dividing by 0 if I plug it in. So I can pull the h out on top, the limit as h approaches 0 of h times 32t plus 16h. And now I can cancel these out and make it the limit as h approaches 0 of 32t plus 16h. Now I can plug in h is 0. That part would go away, meaning it would just be 32t. Because when I plug in 16 times 0, that goes away. So the instantaneous rate of change is 32t, and we wanted it at t equals 3. Sorry, I ran out of room, but we're going to do 32 times t equals 3, which is 96 feet per second, which is the exact same answer that I got on the previous slide. So again, to find the instantaneous rate of change, you're going to use a limit formula, and you're going to shrink the distance between the two x coordinates, and you're going to find the slope in between them. And just a couple of last minute misconceptions that I'm going to touch on now, but we're going to come back to later, so don't worry about this too much at this point. Whenever we talk about instantaneous velocity or instantaneous rate of change, you've got to be using the limit formula. The average velocity, you can just use the slope calculation without a limit. And the instantaneous needs a limit because the distance between the 2 points is approaching 0. When we refer to velocity, it can be positive or negative since it refers to a direction. If you see the word speed, it's just how fast you're moving. So speed will always be positive. Speed's just going to be the absolute value of velocity. All right, I hope this helps. This is it for the rates of change video.